Hello and welcome to another Spotlight with LNG Industry. My name is Lydia Woolworth and I am the editor of LNG Industry. Today I'm joined by a whole suite of wonderful speakers. We have Tobias Eckhardt, Peg Green and Harold Borchter. Tobias is a global technology manager for BASF based out of Nuremberg, Germany, which is one of BASF's main adsorbent production sites. Peg is the global market manager for BASF Adsorption Solutions for the natural gas and CO2 treatment market, based out of New Jersey, America, BASF's Catalyst Division headquarters. And then Harold, who is the Technology Maturation and Deployment Lead for Shell's Gas Processing Department, based out of the Shell Technology Centre in Amsterdam, the Netherlands. So in this Spotlight session today, we'll be recapping and expanding on some of the ideas raised in BASF's recent article entitled Coming Out of the Ice Age. This article details a dual-purpose adsorption technology for combined heavy hydrocarbon and water removal from lean feed gas in LNG to prevent cold box freezing. Tobias, Peg and Harold, thank you all for being here today to talk about the article and dig a bit deeper into the technology discussed.
Thank you. Good afternoon.
Yeah, thanks.
So to start off with, what problem is Durasorb Cryo-HRU trying to solve?
Yeah, thanks for that question. I mean, it's a really good idea to start with the problem and understand what we're trying to do here and why we worked so hard with Shell in order to qualify this technology. Simply put, Durasorb Cryo-HRU is trying to solve the problem of freezing of the main cryogenic heat exchanger in an LNG plant. As you can imagine, freezing can cause some serious issues when it comes to LNG production. So either turn down of the plant, reduced throughput, or even unplanned shutdowns. If we can remove those heavy hydrocarbons prior to entering the cold box section of the plant, we could eliminate this problem. I'd like to turn it over to Harold to speak more from a customer perspective.
Yeah, on a similar line, indeed, in Shell, we have seen a shift in LNG from the more conventional wellhead gas type of projects to pipeline-based projects. And although, of course, when the gas is injected into the pipeline, it's hydrocarbon and water dew pointed. So you wouldn't expect that there are, say, heavy hydrocarbons present, but still, we found out and realized that there is a remaining heavy tail of heavy hydrocarbons. I think mainly of interest in the C8 and C9 region. And although in low concentrations, ppm level, even at these levels, they can still give rise to fouling and deposition in the main cryogenic heat exchanger, so causing a problem. And yeah, we have looked into that after we realized that there is a new challenge ahead. Looked into various technologies and lineups in-house. I think even before we reached out and got kicked off this work with BASF, and then identified actually the BASF Durasorb technology may be the best solution for this problem. And I think that triggered that we reached out and started jointly looking into this.
So as Harold mentioned, this is a problem of heavy hydrocarbon removal, not dehydration. BASF has many years of experience designing sorbide HRUs for pipeline dew pointing applications. Based on this experience, we thought that we could solve this freezing problem and remove the heavy hydrocarbons prior to entering the LNG cold box. We set out to develop a product that has greater capacity for some of the most challenging impurities, which is the aromatics, benzene, toluene, and xylene. Over about the course of a year of intense R&D work, we developed a product with 30% greater capacity for BTX. We thought that this was a great achievement that could actually really help our customers solve this problem. We made a public announcement to the market regarding our capability to remove BTX at a much greater level of efficiency. It was at this point that Shell reached out to BASF and inquired more about our capabilities.
Super, thank you. And now, Harold, would you say it's common practice for Shell to, bring in outside technology rather than to develop it in-house?
Well, I think traditionally Shell was more a company to develop everything in-house and keep it in-house, but I think that has really changed over the years. And anyway, we keep relationship with say EPCs and technology provider regardless. So I think Tobias and myself, I think we go back 2 years before we started this cooperation, just by staying in contact, exchange information on developments, and I think that we leverage that to get in contact. So I think in today's world, Shell really tries to leverage third-party technologies and take them on board, either where we don't have a technology or complementary to what we have in-house. But regardless if we develop it in-house or when we take a third-party technology on board, the technology has to be ready or de-risked, as we say it. That means it must be safe, and it must deliver on promise, on performance. And in-house we call that de-risking, and in case of third-party technologies, we call that technology qualification. But in essence, the process is the same. And in this case, where the two companies work together, we did the de-risking as a joint team. Work BASF and Shell really working together.
So could you explain for us a bit more about the de-risking process and how long it took?
So I can walk you through a quick timeline. So as I mentioned, we made a public announcement about the development of our new product. That was in October timeframe of 2019. Shell reached out to us in November, and by December we actually had an NDA signed. And we were even planning an in-person meeting in January of 2020. We were able to have that meeting, and in retrospect, it's really quite amazing that we were all able to get together in Amsterdam at the Shell Global Solutions headquarters only a few weeks prior to the COVID restrictions getting put into place. We were lucky to have that meeting. I think it set a really great foundation for the team working together, and it really helped to kickstart the project. We worked very intensely over the next couple months. And again, this was over the time period in which, at least on the personal side, we were dealing with a lot with regard to COVID and the uncertainties of the pandemic. But the team was able to stay focused. And again, we worked very hard over those next couple months. And by the fall of 2020, we received the formal qualification from Shell for the Durasorb Cryo-HRU technology.
Do you think that it went faster because you were all, working remotely and everything? Did things speed up?
It's a good question. And in some ways, when I think back on that time, I think it did, right? Because although there was a lot of distractions, especially in personal life, we weren't traveling. And so we were really able to just sit in front of our computers and have those meetings. But honestly, the most difficult part was for our R&D colleagues here in New Jersey. A lot of the work that we did to de-risk the technology with Shell required lab work. And so our lab colleagues, they actually didn't miss a beat. But they did have to come into the office, unlike those of us who work from a computer. So I give them a lot of credit, and that was certainly challenging for them and for this undertaking.
Yeah, and maybe to add to this, what Peg just said, I think, it was good that we could all work from home, so we were not distracted by business travels, but also it was important that we knew each other, that the teams got together before, and that we already had also a developed relationship with each other.
And now, looking at the technology specifically, Tobias, could you give some background of the technology? What exactly does Durasorb Cryo-HRU do?
Yeah, it's a bulky name, right? Durasorb Cryo-HRU. I mean, this technology really was developed to remove heavy hydrocarbons, C7+, aromatics, and clearly also water down to cryogenic specifications, and especially from lean natural gas, where often conventional technologies otherwise used in the industry are ineffective. And this technology basically is replacing a standard MOSIF DHI unit with a dual purpose unit, as we call it, that relies on a aluminosilicate material to do the bulk of the work, and leaves only the polishing duty to the molecular sieve section.
Perfect. And now, Harold, a question for you. So Shell was interested in deploying this technology. Where will it fit within Shell, and how did two large companies work together so successfully?
Yeah, where will it fit in? I mentioned that we see a shift from, say, larger projects, wellhead gas, to, say, projects, LNG projects based on pipeline gas, often also smaller projects, or even, say, linking it to the energy transition. We see, say, bio LNG projects where the gas production and the gas liquefaction are not co-located, so the pipeline is the intermediate. So the pipeline gases become more important. So that is where we see it, and then typically for newer projects. But in addition, we have also identified that even existing projects which currently run only with say molecular sieve dehy units, which see some increase in heavy hydrocarbons in the feed due to maybe different sources of gas being spiked in, they can be retrofitted with not too many complications to go from a conventional dehy to a dual purpose system. I think that's the other application we see. And on your second question, how did we work together? Yeah, I think Peg already hinted at it, and Tobias as well. On the grounding side, there was a relationship. We had a face-to-face first meeting with everyone in the room, and not just the three of us, but the team is actually much bigger than this. Also involves the research assistants on both sides. We have some subject matter experts contributing, so the real team is much bigger. And after this kickoff, we established kind of bi-weekly calls with kind of sprints, trying to progress on all the items. And also important was it was really something say supported by all of us together. It was not BASF to show Shell, but it was really convince ourselves as engineers, all of us, that what we are doing was right, and that we actually delivered de-risking. So that was important. And overall, I think it was fun to do. This way of working and achieving this was fun. And I think that not all work is fun, but this definitely was.
Yeah, it was a lot of work, but I completely agree. It was also a lot of fun, yes.
Yeah, it's good stuff.
Super, thank you. And now, Tobias, how is the Durasorb Cryo-HRU technology process different from a conventional HRU or a standard dehydration unit? And similarly, why is combining the two units a new and different concept?
Yes. I mean, first of all, HRU stands for hydrocarbon recovery unit. So we recover in a adsorbent bed hydrocarbons. And this is usually a short cycle process where the entire cycle of adsorption and desorption occurs in less than 6 for less than 4 hours. In some cases, even less. A dehydration unit where only water is taken out of the gas, on the other hand, is a very long cycle unit, often occurring over the course of, let's say, 24 hours. So the cycle times are so different because the hydrocarbons are not as strongly adsorbed to the adsorptive material as water. So water is way stronger adsorbed. So over longer periods of time, the water in the feed gas will displace the hydrocarbons from the bed. Silica gel materials like BASF sorbate, for example, are used for hydrocarbon removal. These materials are very robust and they often withstand cycles, 10,000 cycles or more in a lifetime. This is very different to a molecular sieve operation where you usually are limited to 1,500 cycles in a lifetime because these materials suffer in wet and high temperature conditions.
Fabulous, thank you. And now, Harold, so Tobias has explained for us some of the challenges. And what was Shell's perspective, and did you see any risks?
Yeah, so we mentioned the de-risking process. So when we sat together at the kickoff, I think we identified many more risks. So it's a high risk, low risk, maybe 10 plus items. But the one that stood really out, I think, is the one that also Tobias mentioned. It's about the mole sieve. The mole sieve layer now will be exposed to many more cycles and much more severe regeneration conditions. And when I explained what the technology was to my peers not involved in the project and saying, yeah, we think we're going to do this, that intuitively, yeah, didn't synchronize. You're not supposed to expose mole sieve to this kind of conditions. You will kill them immediately. It's a violation of every design and operational rule for a mole sieve. So that was really the topic we focused on, and it was about getting the evidence both from the tests done in the labs from BASF in New Jersey, but also when we start digging in our own operational experience. So actually, there was some evidence that indeed under the conditions in a dual purpose system, it could work and a mole sieve wouldn't degrade. So looking forward, we pulled everything together, and we managed to get confidence that this risk that was a blocker perceived from the start actually could be mitigated convincingly.
And that's actually a good point what Harold just mentioned. I mean, Shell brought a lot of experience and expertise to the table, but especially the operational experience from Shell showing that molecular sieves being well protected could last a very long time, also a very important cornerstone for this development.
So Tobias, thinking about your technical team, how did they mitigate the main risks? And also, how can you achieve more cycles using the molecular sieve?
Yeah, so as we just said, I mean, it's all about protecting the more sensitive part of the bed, the molecular sieve, from harsh regeneration conditions. And the concept we came up with was to use more of our aluminosilicate material to reduce the amount of water going to the sieve section of the bed. And basically, then the molecular sieve part is not water saturated during regeneration. And then also the degradation is reduced because you have less hydrothermal stress on the material. And to prove this theory, we ran several experiments to better understand these mechanisms. And first, we put on a hydrothermal stability test to understand the effects of water and having on the stability of the molecular sieve. And the second was what we call a thermal shock test, where a dry sieve was subjected to many heat and cool cycles, many hundred and thousand cycles in a short amount of time. And the results basically were very encouraging, and they also supported what Shell already said based on their operational experience. As long as you protect a molecular sieve, you will gain a very long lifetime. And a cornerstone of this are two materials that are called Durasorb HD. This is a liquid water stable material. And the second one is Durasorb BTEX, which was specifically developed to remove aromatic hydrocarbons, which are a key problem in this application.
Lovely, thanks for all of that info. And now a broad question for you. When are we going to see this technology used in practice, in the real world?
Well, as a general statement, I think I can say that, as I mentioned, the technology would fit in new opportunities as well as in retrofits. But yeah, you may appreciate I cannot disclose too much details of what we have in the portfolio. So maybe Per can say something less sensitive.
So we sold the first license for this technology at the end of 2020 for a plant that will start up in Q3 of 2022. We're very confident in this technology and we're excited to see it put to use.
And we touched upon this briefly already, but how did two large companies like BASF and Shell manage to, come together, complete the qualification so quickly? And what can other companies learn from this successful partnership?
Yeah, I think indeed we touched upon that. So I think existing relationships is a good starting point. In this specific case, I think the expertise and experience of BASF and Shell were complementary. And building on that, we established a joint team. Although working virtually, it was a very motivated, committed team. I think these are the three pillars for the success in this case. And taking it broader, we're looking even at Shell to do similar for other opportunities as well. And I think in general, it's something that can be recommended.
So I strongly agree with the last point made by Harold. There was a lot of respect between the two companies. We both understood the expertise that each brought, right? So we were able to leverage those experiences and those expertise, and we really worked well together as a team. Working together this way was just a much more efficient way to work, and I think that's what others can learn, right? So we had complementary experiences that we could bring to the table and have the most effective and efficient collaboration.
Yeah, and I mean, to add to this, I don't want to have the final word, but like it's, I think it's also about people, relationship, and also trust. And maybe one very personal note from my side that kind of mirrors what Peg and Harold just stated. This was really one of the nicest experiences in my professional life. And because of the people involved, but also because of the meta achieved.
On that lovely note, I think we've come to the end of the Spotlight session. So thank you to Tobias, Peg and Harold for joining me today and adding more detail to your technology.
Thank you for having us.
Before we wrap up, I would just like to remind all our viewers that BASF's article Coming Out of the Ice Age is found in the May issue of LNG Industry, which also has a wonderful front cover as well, also from BASF. So you can access this at lngindustry.com/magazine. So a real pleasure to speak with you all today. Thank you very much. And thank you to our audience for watching.